Hello, everyone. Welcome to this WEkEO workshop. Today is day 2 of our WEkEO workshop dedicated to hydrology studies in a changing climate. Yesterday's sessions was all about giving you an overview of the WEkEO service. We showed you a little bit of what you could find in WEkEO, the data sets, and also very interesting examples of how to use WEkEO. Today is going to be a practical session. And today, as a co-host, there's going to be Ergane Fouchet from Noveltis. And by the way, my name is Andreia Carvalho. Sorry, I didn't introduce myself. I'm a training officer at Mercator International, and together with Ergane Fouchet, we're going to co-host this session. Hello again. Welcome again.
Hi, Hi Andrea. Welcome everyone. Good afternoon, everyone. So yes, my name is Ergane Fouchet. I work at the Noveltis as an ocean engineer, and I am very happy to present this workshop with Andrea.
Yes.
We can have a look at the program of today's session. If everything goes well, which is not sure right now, right after this small presentation, we'll have David Bina, who will talk to us about the WEkEO user support. About the WEkEO viewer, sorry. And then we will have Julia presenting us the WEkEO computing resources. After the coffee break, I will come back to present you the first, the Jupyter Notebook tutorial. And finally, Daria will present you the QGIS exercise. If you're only interested in, let's say, QGIS or Jupyter Notebook or anything, you can only attend the session. We will make sure to stick to the schedule, well, except for the WEkEO viewer, which is unsure for now. But regarding the exercises, you do not have to attend the whole session. So about some guidelines for the Q&A, we're having the webinar on Click Meeting, and on the chat, you can ask your question directly. You just have to put the question mark at the end of your question, and your question will appear during the Q&A session. We will make sure to answer as many questions as we can. Another useful information is that on the top of your screen, you have an orange button that reads WEkEO workshop material. And if you click on it, you will reach the website, this website, the one you see on the slide. And on this website, you can access all the resources, you can access the replays, etc. So all the information you need. Save the link because, you may, after the event, you may need to find some information, and they will all be available on this website.
Exactly. And we will also be sharing with you some useful links on the chat anytime. So don't be shy, post your questions. And for, like Ergane said, for each practical session, we will have a Q&A session as well to answer your questions. So now let's see if David is ready to come in. Hi, David. David, as again said, David is a user support expert in WEkEO, and he will give us do us a little demonstration on how to use the WEkEO viewer. Hi, David.
Hello, everyone. I'm David Bina, working at the WEkEO user support team. I'm glad to present you today the WEkEO data viewer. So here I am on the WEkEO homepage. And if we click here in the header on the data, it will open the data viewer. When you reach for the first time the viewer, there are two layers displayed by default. One product from Copernicus Land provider, and one, the Seawater Velocity from Copernicus Marine. When you are on the tool, you can zoom in and zoom out by scrolling with your mouse. You can grab the map to move left and right. Okay, so let's say for the sake of this presentation, I am interested in the Europe area. I can zoom in a little bit more on the area, on the Europe area. Okay, here at the bottom, you have the timeline to choose to pick another date. And at the bottom right, you have also the depth level to change the depth level. So for example, for the sea velocity, water velocity, if I go to more than 2000 meters, we're gonna start to see the bathymetry showing up. Okay, so let me go back to around the surface. For the example of today, I will take another vegetation product because we are here to speak about hydrology. And I guess that there is a correlation between vegetation presence and hydrology. So to open the WEkEO catalog and search for our product of interest, I can click on this button. It will open the WEkEO catalog. On the right, we have all the products provided by WEkEO. So you could scroll at the very bottom, but it is more convenient to use the filters we have on the left to find our products. So today, I want to take the high resolution vegetation phenology and productivity. So I could, for example, type here HRVPP, and it will filter, and we have 5 products left. And today I want to take this product, but let me show you all the filters we have. So you have some products that are featured and the favorites. You have different sections like the Copernicus services, so climate, atmosphere, emergency, land, and marine. You have the different Sentinel platforms. You have the sensor. So this section was already collapsed, so you can develop or collapse a section. And you have others like the area, the time, and several tags. So for example, I could find my product of interest by clicking on CLMS land because I know that it is the provider of the product I have chosen for today. And also on the tags, I click on vegetation. And here I have 8 datasets left. And I find back the product I was talking about, this one, about the vegetation, phenology, and productivity. It is a yearly dataset. I can click on details to have the details of the datasets. Sometimes we'll find some use cases at the very top of this description page. You can open it and see what this use case is about. At the top left, you have a little thumbnail showing where we have data. So here it is the Europe area. And we have also the geographical extent. Then we have an abstract explaining what we will find in these datasets. And we have other informations of the dataset, so the dataset ID that we can use, for example, when we download data by script, and other information, the provider, the metadata, etc. So now I can click on Add to Map to add the variable I want to choose. So we see here that there are several variables in this dataset. And we can scroll, and I will take the total productivity season 1, for example. So I click on Add to Map, and it is added on the viewer. You can scroll up to close this window or click elsewhere. It will close the catalog. So now in my layers window, I see that I have the 2 displayed by default and the 1 I have added. When you hover with your mouse the title of the layer, we can see the full name of the product and the variable. Under, you have several information like the date, the area, and for example, for the seawater velocity, we have also the depth. Under, we have the color map, so the color used to display the data on the map. And then we have several buttons to customize the visualization of the data. I will focus on the seawater velocity to talk about this button because there are these 2 additional buttons. So from left to right, there is this download button that I will show just after because this is how we download data from the data viewer. Then we have this I button. It will basically open the details page of the product once again, the one we have seen just before. We have this opacity slider to play with the opacity of the layer. So it could be useful if you want to compare, for example, 2 variables within the same area. Let me zoom in just a bit on the Mediterranean Sea. Then we have this button, really useful to change the variable we want to display within the same dataset. So we don't need to open the catalog once again to search for the product, etc. With this button, we already have all the variables contained in this dataset. So for example, I could take another variable like the seawater salinity, and it is automatically updated on the map. But let me go back on the seawater velocity because I want to show you the vectors. You can also convert the color map into log scale by clicking on the log button. And then, because the seawater velocity contains vectors, if you click on this button, you will see the vectors. While I'm zooming in, I try to do it slowly. We can see that the vectors, the resolution is increasing accordingly to my zoom. So it is quite useful. We can see the color, the amplitude of the variable with the color, and the direction with the vectors. Okay, so let me zoom out back to the whole Europe area, and I will, with this eye icon, you can show and hide a layer. So if I click here, for example, I'm hiding the seawater velocity. And if you are not interested at all, you can also click on the cross to remove a layer from this layer window. Okay, now I will talk about these objects on the bottom right. So you have this locate functionality, so you can place some points on the map, and it will display the coordinates that you can copy by clicking on this button. Then you have this measure functionality to measure distance between 2 points. You can also copy the coordinates. You can remove this object by clicking on the cross. And above all, you have this set AOI for area of interest functionality to draw a bounding box where we want to subset the data we want to download, for example. So once it is placed on the map, you can also modify this bounding box. And under these 3 types of objects, you have the settings for the viewer. So if I open it, you can show or hide the base map. You can show and hide the coastline and reference. And you can also change the units, so from kilometers to miles or nautical miles, for example. Now, I will talk about how to download the data from the data viewer. So as I said earlier, it is from this button. Because I wasn't logged in already, it will open this page to log into my WEkEO account. So I log in because it allows me to say that it is totally free first to create a WEkEO account, of course. You don't need to be logged in to visualize the data, but you have to be logged in to download the data. Okay, so now that I'm logged in, I can download the data and specify different parameters to download the data I want. So for example, the first parameter is the bounding box. You can enter manually, manually these coordinates or click on copy AOI from map. So it will pick the coordinates of the bounding box I have drawn earlier. Same for the time range. You can enter manually the dates. You can open this widget calendar, or you can first pick up a date here on the, maybe I was too fast. Here at the bottom, you can, let's say I want data from 2019 to 2020. So here I am in 2019. I click on copy from layer. So, okay. And now I go in 2020 and I click on copy from layer. So here I can see that I'm about to download data from 2019 to 2020. Then the other parameters are not mandatory because mandatory parameters are indicated with this red asterisk, and here it's not the case. So I can leave it like this and download this data. To download the data, you have two options. You can show the API request here. So don't be scared if you are not used to download data via this by script, let's say. Alexandre, we will show you how to do so in the next presentation later today. But just to show you, you can copy very easily the query by clicking on this copy button. And also, you have a documentation, and in our help center, you will find useful articles which will guide you to download the data by script. Okay, but here from the data viewer, we can also click on this button, request data, and then monitor request. It will redirect me into this jobs tab. So I click on it, and here to 20, it's the request I've just made, so it's already completed. I can click on this icon to show the request once again, or I can click on this folder icon to see the different items corresponding to my query. So here it was 1 year of data in a pretty large area. So we can see that it consists in more than 200 results. But just to show you, you can still click on order and then on this download icon, and it will start the download. Okay, but for this case, because I have more than 200 results, I invite you to carefully listen to Alexandre's presentation, or I repeat, go to our help center and to download the script via the HDA API. It will be more convenient. Just to share the information, in this jobs tab, you can see that I already have several jobs. It's because it keeps in this history all the previous jobs, all the previous requests I have done during 7 days. So keep in mind that all the jobs will be removed every 7 days. And now, if you have any question or any feedback, any issue, you can contact us, the WEkEO user support, by clicking on this button. It will open the chatbot. It will open the home tab, and basically you can send us a message or search for help, which are the same as these two tabs here. So you can send us messages from here, and so you can share the issue or the feedback you want to share with us. And you can search for articles in our help center. So here we see the 7 collections existing in our help center. You can browse in this collection, or you can also use the search bar to search. For example, if you have a question about the download, if I type download, I will, here are the results we have. And for example, this article, how to download WEkEO data, will basically show you how to download data from the data viewer or via the HDA API. It's one of the examples of the articles we have on our help center. Also, just a quick important note about the downloading data. For the moment, we are experiencing different kind of issues with level 2 Sentinel data. So some of these projects, level 2 Sentinel data, are not available today, but our technical team is already working on a fix. So it was just a quick note. If you are trying to download this kind of data and have issues, of course you can contact us, but I am warning you already that maybe we'll encounter some issues with level 2 Sentinel data. So I think that's it for me. So thank you for your attention, and I will try to answer to your question.
Thank you, David. That was very nice. That was definitely very interesting to see. And yeah, sure, we do have a lot of questions for you already. Let's start with this one. So I will allow Q&A. First one, Is there a way to explore the catalog filtering out layers which are not visible on the map?
So indeed, there are some layers that are not visible on the map, but you can still download the data. So for example, if I take this is the first one, I add to map, it won't
If
be shown
you
on the map.
if you want to share your
You don't
screen
see
again,
your
you can.
screen.
Sorry.
So remember, on the left-hand side,
Yes,
you will
it's
have the two screens.
on the left. Yeah, it's coming.
Perfect.
Do you see it? Yeah.
Yes.
Yes.
Sorry. So I've just okay. I will do it again. It was just the first product of the catalog. Indeed, if I click on Add to Map, a message will be displayed saying that it can be shown on the map, but you can still use the download functionality to download the data. So I hope it answers the question.
Okay. Great. Thank you. And wait. Okay. In the viewer, can we define an area of interest and save it to use in the future queries?
I don't really know what it means to use it in the future queries, but I mean, if you leave the viewer and come back, I don't know, the next day or else, I don't think the bounding box will be here. But you can still write.
You would have to
or
export
copy
it
paste the
or something.
coordinates somewhere, and then use it in a future request.
Okay. Cool. So another one. Is this one? It's a lot of it, very difficult to see. This is more like a comment.
Yes, because sorry,
I didn't notice.
I don't know which abbreviation, maybe with HRVPP, which was the
okay.
high resolution vegetation phenology and productivity. I said it just once because it's quite long name. Sorry. And then I don't know which abbreviation I
The
used.
ADH API.
Oh yeah, of
maybe
course. Sorry, HDA is for harmonized data access. It's so API. Basically, it's just a way to connect to a server. So we use here at WEkEO the HDA, so Harmonized Data Access API, to do our query, so to download the data via script. But I think that Alexandre will show you this in a moment.
Yes, about that, a little update. So today we won't have Alexandre with us, who's often our. No, that's all right. But we will have Ergane.
Okay, yeah, okay, Ergane.
It's true that it's often Alexandre doing the Jupyter notebooks. Today is going to be Ergane.
Okay, sorry,
but,
my bad.
No worries. But yes, Ergane will tell you more about that later on. Great. I think we have time for one or two more. What about this one? Which are the units of the different HRVPP products? Okay, more abbreviations.
Yeah. Well, honestly, I don't think I can answer now, but you can. I invite you to use the functionality I'm shown to contact us, and then if we have the answer, we will share with you immediately. If we don't have the answer, we will ask the appropriate producer team to provide a correct answer.
Okay. And there's this one. Is it possible to upload a shapefile or raster data? Define my region of study interest instead of using the box, rectangle, or the set of area of interest.
Okay. No. So for now, no, it's not possible to specify a bounding box via uploading a shapefile, but it's feedback we already shared with our internal team. We know that it is a functionality that a lot of users are looking to. So It is an improvement. We have already jotted down. But for the moment, no, it's not possible.
Okay. And this one. Is it possible to change the color of the legend or vector in the viewer?
No, I don't think so. No, we can't change the color.
No.
These are colors by default for each layer.
Yeah.
It changes depending on the layer. So no, I guess the answer is no.
Yeah.
Sorry.
Yeah. Okay. Okay. One last one. Can I do a time series analysis like daily, weekly, and monthly?
I'm
not sure if in this case it's for you. Yes.
I don't know. Yes, I want to answer yes, of course. We can do a time series analysis with the daily data. I don't know if there are weekly data, but you can do a mean of the daily data to get the weekly data. Same for the monthly. There are monthly data, but you can do some calculations to calculate the monthly mean from a daily data set. But I want to answer yes, but the question is a bit general, so I can't answer more than that.
Yes, maybe not necessarily for the viewer, but maybe Julia will enlighten us a little bit more about that later on.
Yes, but once again, feel free to ask us in the chatbot, and we will go deeper in your request, your question, and we will be glad to answer.
Yes. Okay, cool. Thanks very much, David. We will put the link to the user support as well, and also with some useful articles, maybe.
Okay.
Okay.
Great.
Thank you very much.
Thank you, David. Before moving on, maybe some little points. We've had many questions about whether the sessions would be recorded or not. Yes, they are recorded right now. The replays will be available on the material. As I said before, save the link. You will find all the replays on there. For the questions as well, all the questions that we didn't answer today, they will also be on the Padlet, the material. Also the last point we had to tell you is that we advise you not to do the exercise, not to explore the material at the same time as we do it during the live session. That's it. We can move on to the next presenter. Hi, Julia, welcome.
Hi, Ergane, thank you. And also welcome from my side to everyone. So now on to an introduction to how you can access the data and can also make some calculations such as the time series analysis, for example, on the Jupyter platform that is also offered by WEkEO. So I'll start sharing my screen. I will guide you through the different steps how you can access the Jupyter platform. So as David already showed you that you can log into, so you go to wekeo.eu, you can log in if you have an account under sign in. If you don't have an account, then please register, because then only once you have an account you can have access to all the functionalities. So if you go to sign in, you will be asked with your username and password. I also enter here the same, and then I sign in. And once you're signed in, instead of here register and sign in, you see here a set of different functionalities. And here, if you're familiar with Jupyter Notebooks, this is the icon or the logo of Jupyter. And this is where we want to go. So if you go here, if you also hover over it, you see that with this button, you can access the Jupyter Hub. And then if you click here, you will get redirected. And in my case, it already spins up the Jupyter Lab. In your case, it could be that there comes a different step in between where you are asked which programming environment you would like to work on. And you will get two choices. One's the general for Earth observation analysis and the other one for machine learning. This is the case because there are different materials already available that you can also execute and discover on the Jupyter Lab. But for now, for general data access from the WEkEO, you can just simply choose the Earth observation programming environment. This will be enough or sufficient for general downloading data. So once you chose, then your Jupyter Lab environment will be started, and you will see most likely an interface similar to what I have here, but a bit different. So you probably will not see here these notebooks, but you will see folders that like with the name public, probably with public, and if you worked already before, probably also old files. And this is important. So all the notebooks I show today, you also find under the public folder under WEkEO for atmosphere. So if you go under the public, this is also just to let you know, there you can discover a lot of training materials that is already available for the WEkEO Jupyter platform on different application areas. So there is material for atmospheric applications, for climate, for land applications, for ocean, and also machine learning examples. And you find them all here. So for the notebooks I will present today, so if you want to, after the webinar today, if you would like to try it out yourself, then please go to WEkEO for atmosphere, and then again in the folder atmosphere and the folder WEkEO training. And then you see the exact notebook, the same notebooks that I will also go through now. So what I will do now is, so just for everyone, or for those who don't know or are familiar with the Jupyter Notebook interface or the Jupyter Lab interface, so this is your starting environment. So you see here a set of folders, which you can just, as you have it on your working station, you can navigate through. You can also start new files. So like if you go here on the plus sign, a new launcher window starts, and then you can also select whether you want to start a new notebook, if you want to probably start a terminal, if you want to move some files from one folder to the other, or if you also prefer to directly work in a Python shell or Python console. So, and for example, here an example, if I click here, then a new notebook starts. It's per default untitled, and then you can start coding. For those who also don't know a lot about Jupyter Notebooks, the good thing with Jupyter Notebooks is that you can combine code and visualizations and documentation and textual description of what you do in one document. And you can do this by having different types of cells. So per default, and this is indicated by here by the squared bracket, you see this is a coding cell. So if I do a simple example here with print hello world, then you see here, the notebook recognizes Python in the background, and then it can interpret my code. If I want to now explain what this code is doing, then I can go on the menu on top of a notebook here, and this indicates here, says, oh, this is a code cell. If I want to change it, then I can change it to a markdown cell. And then these square brackets disappear, and then I can use general markdown. For example, I use this, this is a heading, and if I execute it, then I have a heading. Or I can also change this to a markdown cell again, and then I can add here just normal text, for example. So in this way, you can set up notebooks, and you can also do your own processing scripts and analysis. This is just a general introduction. Now I will start with the notebooks that are available, and I just remove this again. And I will introduce you today to 3 different data sets that are available on WEkEO. I will show you for each of the data sets how you can retrieve them with the HDA API, so with the harmonized data access, so with an programmatic access directly in your Jupyter Lab environment, so that you don't have to download it on your working station and you have to upload it again. So the data is directly downloaded on your Jupyter Lab. And then I also showcase you an example how you can then directly load this data and manipulate and see how the data is structured and also visualize the data. The 3 examples showcase data from the Sentinel-5P satellite mission, from Sentinel-3 mission, and also data from the CAMS, from the Copernicus Atmosphere Monitoring Service. So I start with the first notebook where we would want to download Sentinel-5P carbon monoxide data, and the notebook is number 10. And so it is structured that for each of the data sets with the first notebook with a 1 and 0 or 2 and 0 is like the downloading notebook, and then the subsequent notebook for the Sentinel-5P one, it would be 11. This is then the data exploration or data discovery notebook. So there are several steps that are required in order to start the WEkEO Harmonized Data Access API client. The first one is to make sure if you work on the Jupyter Lab, it is already installed, but just to make sure that the specific Python library is also available. And you have to, you can just double check if this is already installed. And so just also to let you know that we also linked it here. So it is a Python package that is available. So you can also use it on your working directory or on your local setup of Python. And this is just a package that is that you can use in order to access data from WEkEO. So I start with loading a library because we need this later on because we want to interpret or read JSON files. And then I execute this one, and in my case, it is already satisfied, so the package is already installed. In your case, if not, then the package would be installed. And so once we install the package, then we can also just easily import it. And once we imported it, we can now make use of all the functions that are available and that help us to download data from WEkEO. So David already introduced you to the interface of WEkEO, where you can also browse data and you can also find data. I will also just show you how you can generate the API request of a specific data set you're interested in. So if we go back to the WEkEO interface, we go to data. And then basically, so Sentinel-5P data, so if I just remove this and I go to the plus, if you're interested in Sentinel-5P, you can just look up Sentinel-5P and you can say, okay, we would like to add this to the map. And if we go then to here to the download sign, then we get here an interface where we can specify the data we're interested in. And for Sentinel-5P, there are different processing levels available, a level 1B or level 2. The data I showcase you is for a specific fire event in 2021 in Siberia, and specifically the parameter carbon monoxide can be used to trace fire events when they appear, but this is already on a processed level. So this is after the level 1 processing step, and so that's level 2 carbon monoxide data we're interested in. And so you can choose here the processing level, then you can choose here the parameter or variable you're interested in. So in our case, it is carbon monoxide, so CO. And then you can also specify here the processing level. So anything that is some days back or months back, it is offline, because then all the data is already in one harmonized SWOT data file available. And so we would choose offline. If you don't, if you haven't agreed the terms and conditions, then you have to agree them. And you can also specify here bounding box information. So as I said, for the example we prepared, it is in Siberia and in 2021. And so you can specify here, let's just I just do random numbers just to fill something in and to showcase you the API. I think it was something similar like this. And then also the sensing date, we can, for example, choose 12th of August 2021. And we can also here do 12th of August 2021. And so as David showed you, so if you want to download them from the web browser, then we can go to request data. But we are interested in requesting the data from the harmonized data access API. So we can go to the API request, and you can copy paste this data, this API request. And I'll go back to the notebook now and showcase you where you can copy paste it. So, but just to understand, so all the information what we added here in the interface is now has been translated into a dictionary or JSON format. So we have a specific data set ID. For each data set, there is a data set ID. Then we have bounding box information for west, south, east, and north. Then we have a data range, so like for which days we're interested in. And we also would need to specify here the hours we would like to have data. Then the processing level, the product type, and then also the timeliness. And so with this information, you can also go here then it's copied. Then I go back to the notebook. And so we did the third step. So we selected our data and got our API request for the data we're interested in. And then the next step is to open. So in the folder, you also see JSON files. And this is where we call them descriptor files. So it is a text file which is in a JSON format, and I can open it with an editor. And so basically you can then copy paste this in this text file. You can copy paste your data request, and this is what I did here exactly. So I have here Sentinel-5P. We have the bounding box information. They were similar to what I added in the browser. Then we have also our time period. And I just here specifically also selected the time range I would like to have data. Then the product, it's level 2 carbon monoxide, and the processing level. And then you can save it and you close this descriptor file again. So once you have your descriptor file and you have your API request, then you can start initializing or configuring your WEkEO API authentication. And the HDA authentication is linked with your WEkEO account, because as we said, you can only access data once you're registered. So also the HDA API has to double check that you are registered and you are eligible to download data. And this is done with this line of code here. So we use the client constructor in order to set up our WEkEO API authentication. So we say we want to download data from the WEkEO's data broker. And here where I added the hashes, you can add your username and also password. And with this information, you can authenticate yourself with the Python library, or with the HDA library. And once you did it, then the next step would be to load the data descriptor file where we just saved the API request. And you can do this with the JSON library, where we just say, please load the JSON file. And then we see here again the same values in a dictionary. So we see Sentinel-5P Tropomi. We have here our bounding box information, the date range for 12th of August, and again, the product and the processing level. And with this, then the last step, so then you have all the steps. So you authenticate it, you have your data file, and then the last step is to where we say our HDA constructor, which we called C. So please search for this data which we specified in this data descriptor file, so in this variable. And then the matches here in the variable will first give you an overview of how many data files have been found. And then, because it's in the same cell, it is also directly downloaded. And so this is how you can request one set of data, and specifically the example of Sentinel-5P. And then the data is directly downloaded in your working environment. So once you downloaded the data, so I did it already, then you can open the next notebook, and you can basically, you don't have to, so the data is already in your working environment, and you can then directly start exploring also the data and visualizing it. And so this example now takes the Sentinel-5P data, which we just downloaded. And first, for each Python notebook at the beginning, it starts with loading required libraries. We make use of Matplotlib and Cartopy to visualize the data. And because most or quite a few data from Copernicus are in a netcdf file, we also use heavily Xarray and NumPy. So you will see also that we use a set of helper functions, which I also want to introduce you quickly. So these notebooks, they have a set of helper functions, and these helper functions, they just make it easier, specifically if you're not yet very familiar with Python, in order to also visualize data, to manipulate data, etc. So these functions, they are there for you to, instead of you writing 12 lines of code, that you have in the end a function where you can specify some keyword arguments, and then you can visualize the data. And I'll show you, because these notebooks, they make use of these functions quite a lot. I'm sorry, I try to remove this. Okay, of these helper functions, and then you will also see how they work. But if you already a bit more advanced and expert level on Python, then you also don't have to use these functions, or you can also have a look to these functions and manipulate them, or you can also write your own functions. But anyways, in any case, so you can load external functions or another Python script from a different notebook or from a different Python script to a notebook with this function here. So you use the command %run, and then you can specify the notebook or the script you would like to load. And with this, once we let it run, then basically, this is just like some warning messages. But if we now want to use any of the functions that are available here, so generate geographical subset or select channels for RGB, or visualization function, we can now use these functions and in our notebook. And so the first step, because if we go here under data, I downloaded the data for the example today. So you see there some Sentinel-5P data. So all of them who start with S5P are Sentinel-5P data. And you see that even though they are netcdf files, they are downloaded as a zipped file. And so for this reason, we first have to unzip the file in order to be able to access the netcdf file. And so this is done with this command or with this code block here. So we use the Python function zip file. We specify the data file we're specifically interested in. And then we say, please extract all the data that is available in the zipped folder. So I just also, okay, so I load the functions here, and then if I execute this one, you will see here that, or the data set is getting extracted. Sorry. Okay, so, and so once we extracted the data, we can then open the data set because then we have a netcdf file. And so this is what we do here with the xarray function. So we use the Python library xarray. We use the function open data set because we only have one netcdf file. There is also an opportunity to use more than one netcdf files. Then you could use the function open mf dataset, so open multi-files, multiple files. But because we only have one netcdf file, we can use the open dataset function. And then under the data folder, in my case, I have the extracted Sentinel-5P netcdf file. And important for Sentinel-5P, you have to specify that you want to have the data that are under the group product. Excuse me. So this is a specificality from Sentinel-5P data, the way how they are organized. And so all the information that is of interest and we can also make use of are under the product group. And so if we run this, then we see the different dimensions of the data and also additional what data variables are available. So we see here, because we downloaded level 2 carbon monoxide data, so we have carbon monoxide total column precision, and also carbon monoxide total column corrected. And but also additional information on the dimensions, which are for Sentinel-5P data: scan line, ground pixel, time, corner, and layer. And there is also quite a few additional information available in the data set. So important is, once you load the data set and in a netcdf file, you load a xarray data set. So in order to access the data array and the actual values, we have to load or extract the xarray data array. And we can do this with here at specifying the variable we are specifically interested in. So here and you can do this with using your xarray data set, which we called S5P, and we put the name of the variable we are interested in to extract in square brackets. And so this line of code extracts now the xarray data array, and we see we have the same dimension. So we still have scan line, ground pixel, and time, and also latitude and longitude information, but additionally also some attribute information to know on what units the data is disseminated, the standard name, long name, and also multiplication factor to convert the data to molecules per square meters, because the data is no, to square centimeters, sorry, instead of molecules per square meters, which is the standard unit how the data is disseminated. And so then we can make use of the data that the data file provides us. So we define variables for, or we can have a look on latitude and longitude information. And we can here you also see that we just have one time step. And with this code here, we just get rid of this additional time step, so that we just have for one time step, which we loaded, only scan line and ground pixel information. And then in the next step, we also multiply the data, or we apply this multiplication factor in order to convert the data from molecules per square meters to molecules per square centimeters. We also make use, or want to use, the long name that is part of the attributes in the file name, because this just is also good to use in the, or it's a good standard practice to use in any visualization graphs or visualizations for your data. So we also define a variable here. Then we define the geographical subset, specifically for the area we're interested in. So as a reminder, it is about wildfire monitoring, and specifically for wildfires in Siberia in 2021. And so we set here a smaller bounding box for a specific area in Siberia for this time. And then we apply here one of the predefined functions. So we use this predefined function, generate geographical subset. We only have to specify which data set or which data array we would like to subset, and also the latitude and the latitude and longitude minimum and maximum data. And so then the next step is to convert to apply the conversion factor, which we saved here, or sorry, which we saved here, and then we apply it in order to convert the data to molecules per square centimeters. And then the last step is that we can apply the visualization function, visualize p-color mesh, in order to visualize the data. And so this function combines matplotlib with cartopy in order to bring the data into a nice map, where we also have latitude and longitude coordinate information. And what we have to specify here is the data array we want to plot. So we use our data set that has been converted to molecules per square meters, and we still apply a conversion factor just to increase the readability of the map legend. Then we have longitude and latitude information, then a specific projection, a color scale, unit of the data, the long name, which we use here also from the data attributes, and we add additionally here also the date of the data, then the visualization minimum and maximum range, the longitude and latitude bounding box information, and this the last one is just if it's global data or not. And then you see here a map from Sentinel-5P data of carbon monoxide total column on 12th of August 2021 over Siberia. And we see clearly highly elevated carbon monoxide values over some parts of Siberia, which and this showcases that carbon monoxide can be a good tracer for wildfire monitoring in regions. So the next step I would like, or the next data set I would like to introduce you to is the Sentinel-3 ALGI data. And here it's not, because now we had a level 2 processed product already. For the Sentinel-3, it is, we're interested in a RGB composite, and this can be either true or false color composite. So with this, you can have a look to the notebook that starts with 20, so with 20, and we have the same procedure again. So you probably the download data, the download notebooks, they look quite similar. So we will import first the JSON library. Then if this is your first notebook, then you have to just double check that the Python package HDA is also installed. Then you import the Python package at the beginning. And then you can also search for data sets and get the API request. And the same as we did for Sentinel-5P, we also would do for Sentinel-3. So if I just go back to the data viewer, I cancel the Sentinel-5P and I go here to the plus sign and I look for Sentinel-3. And I look for specifically here the Olchi data. And then you have here again no, sorry, now I have the wrong one. So Sentinel-3 is, there are quite a few data products. So there are data products and also here, so we would look for the level 1, there's full or reduced resolution data. And so if we add this, you then see basically, you can choose also again a bounding box information for when you are interested in the data, the product type, which is only 1, but you can also choose if you're interested in Sentinel-3A or Sentinel-3B. So our example is based on Sentinel-3B and then the level 1 EFR product. And if you also know already specifically, you can also define your orbit number or cycle number. And here it's also good that you work with the area of interest, what also David showed you at the beginning. So if I go back to, and then again, once you have your API request, then you can copy paste it into a data descriptor file. If I open this data descriptor file for the data we would like to download, let me just open it, or I open it here. So this is opened as a JSON file. That's why it's a bit, okay. Okay, so basically we have the same information, so we don't have any orbit numbers, etc. So what we have here is we have our dataset ID, Sentinel-3 Olchi level 1. Then we have bounding box information, again the same area of interest as we had for the Sentinel-5P. Then we have the date range, and here I specifically specified also the time range I'm interested in. So that's why we have a very narrow time range between 3 and 3:15 on the 12th of August 2021. So we set here the timeliness near real time, and then Olchi 1 EFR value, and then from the Sentinel-3B satellite. So if we go back to the notebook, we have our API request, and then we do again the same. So you can here authenticate yourself, and you can start your client in order to request data. Then you can load the data descriptor file once you have your API request. And then the last step is again where we say to our authenticated HDA client to say, please search for this data which we describe in this descriptor file. And then if it finds some matches, so in this data request, it will find one match, and then it is directly downloaded. So if we then open the notebook 21, so this showcases I just removed this because it was just a test for me. So if we open this notebook, you should see the same outline and structure here. So we would start again with loading libraries we need. So it's always the same libraries: Xarray, NumPy, Matplotlib, Cartopy, zip file, because the data is again disseminated in a zip file. And then we also load again the helper functions in order to be able to use specifically also some data manipulation functions, which you will see. So we've Sentinel-3 OLG level 1 data for fire, specifically for fire monitoring. The level 1 RGB composites can be used as a true color, but specifically for fire events, it would be also, or we can also apply a false color composite. So in this notebook contains the 2 examples. I probably will go into one in detail, and then we'll just show you what you have to change in order to create a false color composite, for example. So the data, when you download them, and this is something important, is that basically it has a, if I go here, it has a structure like this. So it will showcase you that it's Sentinel-3B, and but it will end with .sen3. So if you try to open this, it will tell you that, okay, I can't recognize this file because it is actually a zip file. And so in order to programmatically also unzip the file, so you have to rename the data file from sen3. So this is how, this is how it is downloaded. So you have to rename it as zip. And once it is a zip file, the zip file Python library also recognizes the file as zip. And then it can also extract the relevant data. And so once it is extracted, you see that it is extracted in a folder. And then you see here 18 files for each of the channels from Sentinel-3, a specific netcdf file. And I will show you in the next steps how you can use this relevant information in order to create a true or false color composite. So because we have multiple netcdf files, we can use the Python library glob in order to first to list all the netcdf files that are available in a folder. And this is what we do here, just to double check that our unzip functionality or unzip process also worked well. So the data, that everything is there. And the first step is then to open for us to load one single channel, also just to see how the data looks like. So you can do this again with the Xarray function open_dataset. And we just load here the first channel of the Sentinel-3 data set. And you just see that we have like specific number of rows and columns for this data set. But then we can also load all the channel information in one Xarray object. And this is what we would do. This is what we do here. So we apply the openmf dataset function. So here, because it's multiple netcdf files, so that's why we also use the mf dataset function. And we say, please bring all the netcdf files that end with radians, so which are channel information from the satellite, in one data set, and please combine it by coordinates. And so if we load it, we see then here the same rows and columns, but we see, okay, we can't see here the attributes, but we see basically that it is loaded as a data set, and we have here 21 data variables that are loaded and part of this data set. And so the next step is where you can then just use one of the variables. So each channel is now a variable, and you can just see how one of the channel information looks like. So here we load the information from the channel 8. And so the next step is then to also load the geographic coordinates, because per default it is not geographically referenced, what we see here. So we just have a set of pixels with a number of rows and a number of columns. But in the best way, we also would like to bring them onto a geographically referenced coordinate system. And so because if we see here, we also have a net CDF file on geocoordinates. And so this is what we open here. And from this data set information, we can then retrieve the information, only the data for latitude and longitude. And this is what we do here. So from the loaded data set, we load the latitude and then just the data. In the end, we have a list of geographic coordinates. And then we select a combination of 3 channels in order to create a red, green, and blue image. And so this example showcases how we can combine the channel 4, channel 6, and channel 8 into a true color RGB image from the Sentinel-3 satellite. And so for this, we apply the function select channels for RGB, and we say, please use the data set which we just loaded, and that contains all the channel information, and we want to select the 3 different channels. And the result is that we have 3 different variables for red, green, and blue. So we have 3 different data arrays. So here is just one example of the data array. And so once we selected one specific data set, we also have here additional attributes to see that it's like top of the atmosphere radiance of the channel 8 from Sentinel-3. And then we apply some advanced image processing just to make specific features more visible in the image itself. And we first normalize it. So we change the range of pixel intensity, and this improves the contrast. And so we normalize the 3 different channels, red, green, and blue, and then we stack them together into a 3-dimensional data array. So the result, and we use the function numpy dstack, where we say, please bring these 3 data arrays together, and the result is a 3-dimensional data array. And then there is the next step is just we can here have a simple plot of our multidimensional data array, just to see how this looks like. But we see that it's like still quite dark, and we could still apply a histogram equalization in order to improve the contrast. And this is what we do in the next step. So we apply the function equalize adapt hist, which equalizes the histogram based on the histogram values. And then we see that like some features, specifically here, smoke is already a bit more visible than before. And then in the next step, and also this is the final step for visualizing a true color composite, is that we bring this onto a geographic coordinate reference system, and visualize the information on a latitude-longitude grid, and this is how it looks like here. So we apply here the visualize p-color mesh function specifically for Sentinel-3. We also make use here, so we say this is the latitude and longitude information. We have here a title for our plot, and we also use our mesh grid, or which we reshaped to the specific format of the grid. So the color tuple, and with the red, we just use the number of rows and columns to bring it onto a regular grid. And so this is a true color composite over Siberia on 12th of August. We see here smoke. We can use also a channel combination for Sentinel-3 to have a false color composite. And instead of channel 8, 6, and 4, we apply the channel 17, or we do a combination of channel 17, 5, and 2. And this would allow us to have a false color RGB composite, which showcases healthy vegetation in red and any smoke in brownish. And so this is here just the intermediate plot, and then the final plot on a regular grid clearly showcases strong smoke patterns here on the over Siberia. And yeah, with this, I would go to the last data set. And this introduces you to data from the Copernicus Atmosphere Monitoring Service, and specifically the global reanalysis data set. Here again, it's so this is model forecast data, so it's not satellite data, but this is the strength of WEkEO because it has different data types available and tries to offer a harmonized data access from different data organizations and data types. And so how to request the data is the same. So you would first look for the data set in the data viewer. So here you can look for CAMS. And there are quite a few different data sets available because CAMS offers also forecast data. But the data I introduce you to is the CAMS Global Reanalysis Forecast, which is a climatic or climate data set that goes back to the past, I think it's past 20 years at least, of global atmospheric variables. And so if you add this to a map, then, okay, I remove the old one, and then I just open this here. And so the specificality for CAMS data is that there is a lot of variables available, what you see here already. So you also have to specify the date and also your bounding box information in the best case. And then there's the parameters on single levels and also multi-levels. So multi-levels means it could be pressure levels, or it is on pressure levels. So if you do specific scientific studies on pressure levels, then you would be interested in on multi-level data. For the example we prepared, we're interested on the surface. So this is only on the surface level, which means single level data. And because it is for wildfire monitoring, so we specifically focus on the parameter organic matter aerosol optical depth at 550 nanometers. And then there is additionally also a lot of parameters. And then if we scroll down, so you can also see here, then you can select the pressure levels if you choose a parameter that is available on pressure level. You can also choose a model level if you're more interested in the model, model or scientific studies of model comparisons. And then you see here that the data is available every 3 hours, and you can choose the data or the times you're interested in. And then you can also choose the format if you're interested in NetCDF or GRIP. So GRIP, for those who don't have a meteorological background, it is a specific data format and a very efficient data format to exchange data files within meteorological organizations. But you need specific software in order to be able to read GRIP data. And so that's why the CAMS data or CAMS also offers NetCDF data because it's easier to read and write for, if you don't have specific GRIP software. And then here, you can also open, again, the API request. And then I go back to the notebook and I showcase you the API request for the CUMS data. So if I open this, we see here again the dataset ID, which is CUMS Global Reanalysis. Then the data range is also the 12th of August for the entire day. We have here the organic matter aerosol optical depth parameter, the time. We specified every time that is available on that day. And we specified also that we would like to get the data in NetCDF. So, and then if we go back, so yeah, once you have the API request, it is the same again as we had before. So you have to start your client by authenticating yourself with your username and password. You have to open the data descriptor file, and then you can say your client, please search for this data, and then download the available data set you find. And then the last step is to also showcase just how the data is structured, and how it can be visualized. Here again, so we just load a set of libraries we require, and also some the helper functions again. Because it is model data, it is usually, or the advantage we have, it is compared to satellite data, very structured. So it is already on a regular coordinate reference system and latitude and longitude grid. So, and we can just download or open it with NetCDF. Just as a note, so if you download CUMS data, you will get a data set that will start, or the name will start with adapter.mars.internal. And this is what I changed. So I changed or renamed the data set to CUMS EAC data, for example. So that's why, but if you download it with the HDA API from CUMS, you will get a data set that with a quite rather cryptic name. So you might also want to rename it. And then once, so we can just use xarray open _ dataset function to showcase or to open the data set. We see we have 3 dimensions, so 8 time steps and latitude and longitude information, and 1 data variable. So we see here the organic matter aerosol optical depth. Then we can see here that the time for the file, the latitude and also longitude. Here, a particularity of often model data is as well that they are on a grid from 0 to 360. But xarray can interpret the data, so we don't have to change anything, but sometimes it can happen that you only see half of the data, depending on how you plot it or visualize it. So in this way, you would need to move the data from a 0 to 360 grid to a -180 to 180 degrees grid. So we then load from our data set again the data array. Here we do it as different. So instead of adding it into square brackets, we just add a period and then the name of the data variable. And this is the same, it has the same functionality. So we have then our data array, again with 3 dimensions and additionally units, because it is aerosol optical depth, it is unitless, and we also have our long name. And so we store this information also as variables, and the same we do for latitude and longitude information. And then, because it is model data, we already have all our information ready in order to be able to visualize the data. And so we can apply again the function visualize _ p color mesh, specifying the data array we want to visualize, longitude and latitude, projection, color scale, units, long name, then the range of minimum maximum values to show in the plot, and if it's global data. And in this case, we can set it to true because we didn't specify a bounding box. And then the result is that we see also elevated organic matter aerosol optical depth values over Siberia on 12th of August 2021. And yeah, so with this, I would basically stop my data demonstration and would hand back to the WEkEO event team. Thank you.
Thank you, Julia. Thank you very much. That was a very detailed presentation. I think it was super interesting, and there's loads of questions for you right now. So let's start with our Q&A. Ergane, if you're there.
Yes,
oh yeah, I can see you now.
here.
Yes. I'll leave the questions for you then.
There we go. First question, easy one. Are the Jupyter notebooks available? Can you remind us where they are located?
Yeah, so the Jupyter notebooks, so if you access the notebooks directly from WEkEO on the Jupyter Hub, you find them in the public folder. Or I can also paste in the chat on GitHub the same notebooks that you find on the WEkEO Jupyter Lab. They also stored on GitLab. And I will just paste the link to GitHub as well. So you find them on these two spaces.
Okay, thank you. Next question. Someone trying to modify and save the Sentinel-5 request, but I think it's because they're trying to save it in the public folder. This is why it didn't work.
Yeah, so this is with anything you do in the public folder, I recommend to make a copy of the folder in your own workspace, because then you can also make modifications to it. Because public, it is like only read-only. And this is exactly the problem. So if you make some changes, it's saying you can't. But if you make a copy in your working directory, then you can save or make changes and save the JSON file.
Okay, thank you. Question about the storage, RAM, and CPUs. How much can we ask for?
I think this is a question for David. I don't know.
Well, I can say that's very variable, but you guys can check the different plans that are available on the WEkEO website. We can also post the link here. But yes. I wouldn't know how to say it from the top of my head, David, if you know the exact RAM.
As you just said, there is a pricing table on the WEkEO website with different possibilities, options. And then if you want to have a custom tenant with a custom CPUs and RAM, just contact us, the WEkEO user support, and I will fulfill your request.
So you mean it can be adapted to
yes.
Each person's needs, or is it? Okay.
Yes, we can create a custom request.
Okay, cool.
Okay, thank you.
I will leave you the link here. Thank you.
Okay, how can you embed other libraries from GitHub with additional features? Could you do it?
Okay, so if I understand this question right, is basically if you can install other libraries that are available on GitHub or on pip or Conda. So yes, like it is really a working environment. So that's why you also have a terminal. With the terminal, you can set up your environment. If there is already a default environment installed with the most used geospatial Earth observation libraries available. But if you need additional ones, then you can install libraries that are hosted on GitHub or on pip or Conda via the terminal. Or you have to say the example what I showcased you in the notebook as well. So you can also do it in the notebook directly.
Okay, thank you very much. Next question then. Is it possible to filter by Sentinel to tiles in the HDA library?
So I'm not an expert on Sentinel-2, so I don't know if maybe David knows about this and can get a bit more specific answer, because I wouldn't be able to respond to this.
I'm not really an expert as well, but for this question, I would say that it is not possible to filter by tiles for the moment in the viewer, but as I was saying in my presentation, this kind of feedback is always welcome, and we note them and for future improvements of the viewer. But the answer is no.
Okay,
But
thank you.
in the HDA library, you can, in fact, you can select items by item when you are downloading via the HDA API, and the item correspond to a specific tiles. But you have to maybe look at which item gives which tile. So with the HDA library, it's a kind of possible. It has to be double checked, but so maybe the answer is yes.
Okay, great. Thank you. Okay, I'm not sure about this one. How do you cite maps created in WEkEO? Can you use them in publications?
Same you have in the data viewer in the settings that I have shown at the bottom right. If you open the settings window, you have also a paragraph explaining how to cite WEkEO. And yes, you can. I guess you can use it in publication as long as you cite WEkEO. But once again, it has to be double checked.
Okay. Maybe one or two last questions. Could we download the visualized Sentinel 5P as TIFF files or JPEG images?
Yes. So it's directly from the notebook. I think there is no. It's actually. So there's just a command that we can just say, okay, from this graph or from this output we can download it. It's a good point that we will integrate this into notebooks that people can then also see how to download it. But I don't know it out of the top of my head. So, but I promise you to integrate it. So if you look to the material, let's say in the next week, then you will also see an example how you can download it. Or for now, you can also make a screenshot yeah.
There was a question about an R kernel that it isn't available yet, and I think Sabrina was asking. Sorry to interrupt. It was just I saw that she asked again. I think she was asking if it is possible to demand R kernel. I'm trying to find the question again. Or
Yes,
Sabrina, if you
yes,
yes.
I already tried to answer. I don't know
Oh,
if it's
okay.
the same person, but
I think so.
indeed there is no R kernel for the moment. But normally you can launch R in a terminal in the Earth observation server and not the machine learning server.
Thank
And
you.
if you still have issues to launch R, as always, contact us, and we will see together the issue.
Okay, great. I think that's it for the Q&A session. We will answer the rest in the Padlet, and we'll provide the answers to you.
Yes.
Thank you very much, Julia, for this very extensive presentation.
Thank you.
Yes, thank you very much. Bye-bye. And yes, so now we will go for a quick break. But before we go, we have a few, just a few information to give you. So first of all, yes, there will be a survey. Thank you. No, that's okay. Yes, there will be a survey. So during this break, we would like to ask your opinion about what you have seen so far to yesterday's session and today's as well so far. This survey is really important. It can help us improve our workshops and think of new topics to bring to you. And some other information is that after this break, we will have Ergane, who will introduce us to a Jupyter Notebook tutorial, which is going to be about a little bit more specific for this workshop today, so on hydrology, and it will be about the droughts in 2022 in Italy, if I'm not mistaken. Yes?
That's it. Yeah.
And thank you, everyone who has answered our short survey. This is very nice. We will have a more complete survey that we will share with you on the Padlet later on. And so that will help us a lot. So now I will introduce you to Ergane, who you already know from our workshop. So Ergane will, like I said, she will do a tutorial about about the droughts in Italy in 2022 using Jupyter notebooks. And so the floor is yours, Ergane Fouchet, whenever you want.
So the exercise I'm going to present you will be available on the Jupyter Hub, and you will find on the Jupyter Hub the same way as Julia presented you just before, and you will also find on the Padlet, so on the WEkEO material that you have on the top of your screen. Save the link, please do it. You will find all the information to access this exercise. So, oops. Right now, the notebook is not available yet. We are going to upload it at the end of the week probably, but I'm going to present you what it will look like. Before we start, I would like to point out that this great exercise has been developed by a colleague of mine, Alexandre. And so all the reward must be addressed to him. Yeah. Once you reach the Jupyter Hub, you have to pay attention and to use the right kernel to have the good environment, and the one you need is the mini WEkEO lab, this one. Yep. And so, yeah, Julia already told you everything about how Jupyter notebooks work. So to run a cell, you have to click on the arrow, or to use the keyboard shortcut Shift and Enter. You can restart the notebook if it doesn't work, thanks to the restart kernel here. And I think that's all for the introduction to Jupyter notebooks. Here's the program of the exercise. So I'm going to introduce you to the subject of the exercise, that are droughts of summer 2022. Then I'm going to present you the libraries, the Python libraries we will use. We will teach you, although Julia already presented you an extensive presentation of this, we will show you how to open and explore some data. We will study the snow deficit in northern Italy, the precipitation anomalies in Italy again, and then we will visualize the consequences of the droughts over the Po River thanks to satellite images. So that's it for the program of the exercise. So if you live in Europe, or if you watched the news last summer, you have probably learned that Europe suffered a very intense drought period in summer, well, last summer. This drought was due to low precipitations and very long heat waves, and it covered, well, the whole Europe suffered from this drought. On this map from the European Drought Observatory, you can see that all the indicators showed that the drought was very severe. So you have several parameters that are the rainfall deficit, soil moisture, vegetation stress, etc. So all the parameters indicate that the drought of July 2022 was very intense. So droughts have, of course, very negative impacts on many aspects. They have consequences on the water availability, on hydroelectricity, on agriculture, of course. And because these events are expected to become more likely and more severe due to global warming and climate change, it's crucial to learn how to assess their impacts and to assess such events. So this is what we're going to learn in this notebook. We're going to learn how to measure hydrology parameters thanks to the WEkEO portal. And that's it. So we're going to use basically the same libraries as Julia presented you just before. So these are very basic libraries for Earth observation. We're going to use NumPy, Xarray, Matplotlib, Cartopy, Rasterio, and GeoPandas. On this table, you can find the link to the documentation of each library. Besides, they are very commonly used libraries. So on the internet, you can find plenty of examples of how to do maps, etc. And if you have any question, you can also send a message to the user support. So you should have everything you need to do whatever you want with the WEkEO data. So here on this cell, we import all the libraries. And then we can start exploring some WEkEO data, starting with some ERA 5 model. So the model we're going to use is the ERA 5 land monthly average data from 1950 to present. So this product is a reanalysis data set. It combines the advantages of a model with the advantages of some observations. So it's a very reliable product. If you click on the link here, you will access plenty of information about the product. So yeah, don't hesitate to have a look at this page. And the variables that we're going to study here are the total precipitation, the snow depth, and the snow density from January 2000 to December 2022. Here are some information about the product. We have the spatial and temporal resolution and temporal coverage as well. So if you need to download the data, so yeah, Julia already showed you plenty of things. You can, of course, download it through the data viewer, selecting the bounding box, the variables, etc. Julia already showed you this. But in this notebook and in this workshop, we would like to teach you how to download the data directly from Python, thanks to the HDA Harmonized Data Access API provided by WEkEO. On this cell, as Julia said before, you need to be registered to the WEkEO service to access the data. And thanks to this cell, the notebook will know how to access your username and password. So if you run this cell, the cell will ask you to enter your username and enter your password, and then you'll be all set to download the data. What we're going to do is that we're going to download the file thanks to a request, exactly the same as Julia showed you before. If you select all your parameters on the data viewer and then you click on Show API Request, so of course I didn't select anything here, but if you select your parameters, you will find all the data you need. And here the request we have for our study is already available in the Jupyter Notebook folder. It's called era5rec.json. If you right-click on it and open with the editor, you can access all. But you can also see what's in it thanks to this little cell. And here you can see we download the years from 2000 to 2022 and all the months below. For this presentation, I'm not going to download it in real time because it takes some time and I want to save time to present you plenty of things. But if you uncomment the following lines you run the cell, the ERA 5 land dataset will be downloaded here in the data folder on the ERA 5 land folder, etc. Well, fine, you shall retrieve exactly the same folder as me. If you explore if you have a look at the request, you can see that we have asked to download the file in the GRIP format. That's something we choose for the notebook to be more convenient. And if you try to open the file with the XArray, which open dataset function, you will find, well, you will need first to specify that you're going to open a GRIP file. So you have to put this. But if you run this cell, you will have an error and the code will advise you to add one of the following keys. So filter by keys, you have 4 options and we're going to use the 4 options. And actually, for each of the filter by keys option, you will retrieve one part of the dataset. So I'm not going to be very extensive on this. The text is very clear and I want to spend more time on presenting you the results. But with the first filter by key option, we have the precipitation from 2002 to, we have the precipitations from 2002 to 2022. So that's the first option. If we do with the second option, you will see that we have, again, the precipitation. You can see TP here refers to total precipitation. So yeah, here it goes from 2000 to 2002. So if we concatenate the first 2 files, we will retrieve, that's what we do here, we will retrieve the total precipitation for the whole period that we wanted. Then we open with the third option in order to retrieve the snow depth. Again, if you have a look, you have the snow cover and the snow depth in these 2 variables. And yeah, so the snow depth is divided into 2 step values, but if you have a look at the notebook, it will explain you how we can fix this issue. And finally, if we open the with the fourth option, we will retrieve the snow density. Here, RSN stands for, if you check, snow density. Okay, so now we have our 3 dataset. We have the total precipitation, we have the snow depth and the snow density all ready for us to explore. If you need to select a variable, well, one of the main things you need is to manipulate the XArray dataset. If you want to select one variable, let's say time, for example, you just have to put the name of the variable between brackets. Here, if you run this cell, you will retrieve the values of the time. If you want to select one date, one exact date that's included in the dataset, you have to use the .cell method and put then time equals the time you want. And if you run this cell, you will see that now the cell does not have time as dimension. The dataset do no longer have time as dimension. We only have one date time, that is June 2022. If you want to select a date, but the date is not included in the dataset, for example, if we would like to have the 5th of June, it's not possible because the dataset only takes the 1st of the month, so it wouldn't work if we remove. You will see you have an issue if you run this cell, but if you put method equals nearest, well, maybe I shouldn't have done this. Okay, I promise you it works. Sorry, because I would have to run the previous cells, but I will follow on. And one last method you can use if you want to select a date from its index. If you want, for example, to take the 9th date time, you have to use the .icell method. And here you have the result, and the 9th date time will refer, as you can see here, to October 2000. So that's it. Finally, if you want to select a time range, you can use the slice method. So again, you still use the .cell method and slice. Here we take from the 1st of July to the 31st of July. And because there's only one date between these two dates, you will have again one date time. Okay, so now we have seen how to explore dataset, how to select variables, to select only one date time. Of course, you can apply it to any other dimension, longitude, latitude, etc. You can select, subset your dataset as you want. And now we are going to plot a map. We're going to plot the total precipitation over Europe in October 2020, according to this product. So first, we defined the area of interest of Western Europe. So these are the coordinates of the bounded box we want to plot. And so what I would like to do is first to show you the figure and then to explain you how it's been constructed. So that's what I'm going to do here. The result is this. So we have a map of the precipitation on October 2020 over Europe. Kind of easy. What we do is that first we defined the date we want to plot, so October 2020. We select the total precipitation. As we have seen before, it's called TP in the dataset. Then we select the date with the method we have seen just before. Then we use some matplotlib functions to create knife figures. So here we create the figure, we add the coastlines, we add the grid lines, we remove the labels on the right and on the top, we add the landmass, and we set the extent according to what we have defined before. Then we use the pcolor function to display the precipitation. We add the title, the color bar, and we set the labels. If you want, you can save the figure. And that's it. So we can see on this picture, this figure, the regions where the precipitations were the highest, and it seems to be in the Alps in Italy. So this is the region that we are going to study. We're going to study now the snow in northern Italy. Italy is one of the countries that particularly suffered from the droughts of 2022. And one of the reasons for this drought is the snow deficit in the Italian Alps. If you click on this link, you will have a EUMETSAT article that covers the subject. And now we're going to see how, with the ERA 5 dataset, the one we just downloaded, how we can observe this event. The first thing we want to know is is to extract the data in Italy. As you have seen before, we downloaded the data for all European continents. So we want now to select only Italy. And to do so, we are using a shapefile from Eurosat. And it's again, it's stored in the data folder of the notebook. If you run this cell, you will observe all the information of this data of this shapefile. So you have all the countries and many parameters that describe the countries, and one of them is name English, which we are going to use to select Italy. So if you run this cell, you will find the information about Italy. The parameter that we are interested in is the geometry that gives the coordinates of the polygon that describes Italy. And if you run this cell, we will color Italy to verify that we are watching the right region. So it looks like Italy. And to plot this map, we use the dot plot method. That's it. We are going now to extract the data sets that we have. So the precipitation, snow depth, and snow density, we're going to subset them to study only Italy. So that's what we do in the two cells here. At the end, we have the precipitation, snow depth, and snow density only in Italy. And we are now all set to monitor the snow cover in Italy. So first we'll have a look, we'll create a map of the snow depth in Italy in January 2022. So again, first I show you the map and then I show you how we constructed it. So here is the map. So you can see there are more snow in the Alps, and we have no snow near the coast. So how did we build this figure? Again, we selected one date. We selected the snow depth from our data set. We selected the time as well. We applied this filter so that if the snow depth was equal to 0, it is not displayed on the map. So it appears in gray. Again, the characteristics of the plot. P-color function to plot the region where there's depth, and titles, legend, and say figure. So that's it. What we are going to see now is we're going to calculate the snow water equivalent, which is a parameter that describes the depth of water that would be if all the snow melted. So this parameter is calculated multiplying the snow depth per the snow density, and then you divide it per the volumic mass of water. That's the formula. That's what this cell does. And we can plot the evolution of the mean Italian seawater equivalent over the last 20 years. So this is what this cell does. And that's the result of the figure. What we do here is that we calculate the mean. So we have calculated the seawater equivalent, and we average it with the dimension latitude and longitude. So we only have a value that depends on time. And we can plot with Matplotlib. It's kind of easy. So what we can see from this figure is that although 2022, the winter 2022 was not the least we've had over the last 20 years, it's still pretty low compared to some previous years. And so this is one of the reasons why that explains the droughts that occurred in summer 2022. But because there was not as much snow in the Alps as for the previous years, but we've had droughts in summer. Now we're going to study the precipitation deficit in Italy in 2022. So we're going to plot the anomalies. Because besides the low snow, we also had low precipitation in spring 2022. So What we're going to do is that we're going to compare the last 3 years, so 2020 to 2022. And we're going to compare these 3 years to the last 20 years, so from 2000 to 2019. On this cell here, we select, we're going to study only the month of May. So we compare May 2022. That's what we do here. We select May 2022 and we compare it to May. So that's here we select only the month of May, and here we select the month of May for the years 2000 to 2019. Then we can subtract, plot the difference between these two dates. And again, I'll show you the map. Here you have the precipitation anomaly between May 2022 and the average of May from 2000 to 2019. That's how we go. So as I said, you subtract the two datasets that we have defined. You define the characteristics, the landmass, etc. Pick color to plot the anomalies, titles, and legend. So the first analysis we can make on this map is that obviously the precipitations lacked in, well, over almost all the Italian region, and especially in the Alps. We can see very low values here, very high anomaly. And so what we are going to see now is that we're going to see, this is just for the month of May, and we're going now to study for, well, month by month, we're going to see how it evolved. So again, we're going to select the historical reference data set. So we select the precipitation in Italy from 2000 to 2019, as before. We group by month. And if you have a look at the result of this, you can see that we have one value per month. And for each month, you will have the mean, the temporal mean over all the years for each latitude and longitude. Now we do the same, but for the last 3 years. Well, we don't compute any mean, but we select from 2020 to 2022. And for these two data sets, so the one, the historical one and the last 3 years one, we can calculate the mean so that, again, we only have a value that depends on time. We calculate the mean over longitude and latitude. And, well, again, I'll show you the chart first. It will be easier to explain. What we are plotting now is that we compare for each month from January 2020 to December 2022. We compare each month to the historical mean 2019. So to do so, we are using the .bar function from Matplotlib, and we set the labels, etc. And so again, as we can see, the last 3 years have been very low, very well. We can observe a very long-lasting deficit in precipitation, and especially in 2022. So this analysis, the low precipitations combined with the low snow depths, explain why the summer 2022 experienced a very severe drought. One last analysis about the precipitation. We're going to compare the yearly distributions. Again, I show you the figure first. So that's the figure that we're going to plot. To plot basically, what we plot is the almost the time series of the precipitation, except that the months are sorted by so that the curve is only increasing. So that's what we do here. On this cell, first we sort the months so that the curve is keeps increasing. And the result, the analysis that we can make is that again, 2022 seems to be a very exceptional low precipitation year. It's lower than all the 20 previous years. Okay, so now that we have seen why the droughts appear and that we are able to monitor why droughts appear, we can see the consequences on hydrology, the consequences on river flows. And we are going to use satellite images, and we're going to focus on a smaller region of Italy near the city of Cremona. And that's it. And we are going to use the Sentinel-2 images with a resolution of 10 meters. And we're going to use 2 dates. But first, let me show you how you can download the file. As David said before, the requests for Sentinel-2 don't really work for now, but they are going to be fixed soon. So when it works again, you can use the following cell to directly download the Sentinel-2 images you need. And if you need information, you have the link here to the tutorial that will explain you all you need. So, as I said, we're going to define this small region in the north of Italy where the Po River, which you see here, and where it flows. And so I'm going to present you a little how the Sentinel-2 images work. So because it don't work, the downloading application doesn't work here, we have downloaded it on our site. So we have downloaded 2 files, one from July 2021 and one from July 2022. And the aim of this analysis will be to compare the 2 years. If you have a look at this these images, you have to go through the granular here, images, 10 meter, as I said, resolution, and you will see that you have several tiles, and we have a little plot about how the Sentinel-2 images work. So the band 2 refers to the blue color, then you have the green color, the red color, and the near infrared color. These are the files that we are going to use. And so here in this cell, first we defined the links to the path of the tiles that I presented to you for both 2002, 2021, 22, 29. We open this file thanks to the raster methods, and then we can visualize the drops. So first, we're going to use all the tiles to have a real image and to compare the two images. That's the result of the cell. So as you can see, the first thing we can notice is that this picture on the left, which refers to 2021, looks more green, whereas in 2022 it looks more yellow, meaning that the soil here is wetter, whereas this one is drier. So that's the first sign of the drought that we can observe. But what we are going to do now is that we are going to see where water, we're going to compute the water mass on the two images in order to compare the flow rate of the river. So to do so, we are using the NDWY, which stands for Normalized Difference Water Index. It's calculated using the near-infrared and green bands of Sentinel-2. And so this is the formula, and this is how we apply the formula to the two data sets. I think that, yeah, there's something I forgot to say, is that since January 2022, the Sentinel-2 products have a new processing baseline. They have an additional radiometric offset that is set to 1000. And if you want to compare the two images, you have to apply the offset. So that's what this cell does. In 2022, we apply the offset. So we reduce per 1000 the values. So then the NDWY values will be correct. And here is the result. So this cell shows the mask, the water in 2021, 2022. And we can apply a filter so that we only see the values that are above 0. And here for 2022, for example, this is the regions where there was water. What we are going to do finally is to compare the two masks. So we're going to subtract the two masks. That's what we do here. So we water change this value. We compute the water change. And that's the result. So in red, you have all the regions where we had water in 2021 and we no longer have water in 2022. So the difference is kind of obvious on the figure. And so, yeah, large portions of the riverbank were covered in water in larger portions were covered in water in July 2021. And so this figure highlights the consequences of the droughts over the Po River in the sea. So that's the end of my presentation. So just to summarize what we have learned how to access the Sentinel data, the WEkEO data, sorry, how to monitor the precipitation, the snow, and the snow depth. We have learned how to visualize the impacts of the droughts over the rivers thanks to Sentinel-2 data. And so we propose to use several exercises so for beginners and for intermediate level, which will teach you how train you to use the codes we have prepared for you and the data as well. And I think that's it. If you have any problem with the notebook or with the exercises or whatever, do not hesitate to contact the WEkEO support and we'll be very happy to answer. And I think that's it. I don't know if we have questions, Andrea. You're mute.
Yes, we do have some questions. Thanks for this very detailed explanation. That was very interesting. It's quite impressive to see the difference between the 2021 and 2022. That is quite alarming. We do have questions, and the first one I will share with you, which is the difference between your calculation and the ERA 5 land snow water equivalent? If you're aware of that.
Question, but yes. Not really. It's a trouble now with click reading. I don't know why.
Oh.
But
anyway, is this the sound we're hearing? Yeah.
I don't know.
Can you see the screen? Okay. Yeah.
I can. I don't know why they want me to show my screen.
Because here we
anyway, I can
see
hear
your screen.
You.
Okay. I will just read the question. No worries.
That's great. Thank you.
Okay. So next one. The used data are L1C or L2A?
I think the L2A, but I'm not sure. I'll have to check. I'll answer more precisely in the document we'll provide to you after.
Yes, and you will also be able, just to remind you, that at the moment, like I again said, at the moment the tutorial is not available yet, but at the end of the week it will be on the Padlet, where you will be able to access the document, and you will be able to practice on your own at your own pace, and you will also have access to the recordings of today's and yesterday's session, so you will be able to see it and explore it again at your own pace. We have one or two more questions. Where can we get the data and the script? Okay, yes, that's what I just answered. So later on will also be available, this notebook will also be available on the Jupyter Lab and GitHub, like Julia showed you before. So we're still working on that, but it will come. And I think it's all related to the Jupyter notebook.
That's because people couldn't do it at the same time with me.
Yes, yes, I guess they would have had many more questions, but
I think so.
it would have been very chaotic as well, I guess. So it's better to do one thing at a time.
Yeah, sure. I agree, yes. And
Yes.
anyway, you will, between today and the briefing session, you will have plenty of time to do it. And if you have questions, I and Alexandre will be back to answer them. So yeah, do not
Exactly.
hesitate to have a look and to ask us questions.
Yes, don't be intimidated by the level if you're a beginner. So give it a try and come with your questions. If there's no stupid questions, so we will all be there to answer your questions. And there's no limit of time. These resources will be available even after the briefing sessions. So, okay, thank you very much again. And
Thank you.
I think now we will welcome Daria Andrievskaia from Noveltis as well. Hello, Daria. Welcome again. And so today, Daria will give us a short demonstration of on QGIS, how to use WEkEO data on QGIS. And if I'm not mistaken, you will show us some sort of analysis of the floods of Pakistan, right?
Yes, exactly.
The floor is yours whenever you want.
Okay, great. So, hello everyone. My name is Daria. I work at Noveltis, and today I'm here to do a short presentation on how to use WEkEO service products in QGIS, and we will focus specifically on a study of 2022 Pakistani floods. So I have very not much time, so I'm not gonna be very precise. So if you want to see more in-depth instruction how to do this, how to follow this tutorial, you can find the video on a Padlet, and also later you will have access to a PDF version of this tutorial, which is even more more precise. So we're going to study Pakistani floods, which happened, as you may know, at the summer of 2022, which caused a lot of damage, and of course, a lot of people were killed, and yeah. So we're going straight to QGIS. So here, what I want to say very briefly that I already did this project, so I already did all the exercises. So I'm going to just shortly show you the results of several functions and features of QGIS. And again, you will follow it if you want. You can follow it with a video or PDF tutorial. So I'm not gonna stop on how to download data because you've been already instructed how to do that. Here we use two types of data. First is a river discharge. So it's gonna be we're gonna import it as a raster data, and also we're gonna work with satellite images as raster data. So we have two exercises, and first is going to be exactly about the river discharge. So river discharge is basically the amount of water which passes through the river per specific unit of time. So that's been done. Is the river discharge has been mapped, and the style has been adjusted. So here, for example, you can see that blue corresponds to 0 river discharge because there are no rivers, and you can clearly see the footprints of rivers. So here, this one corresponds to the 30th of August 2022. We have time frames from 1st of June of 2022 till 10th of September. And on this this exact time frame, we chose for further analysis, just because it was having quite extreme values of river discharge. You of course can play with any other date, or maybe with all of them if you want and you have time. So here you can see the scale, and you can see that this river here in very, very red has a very big, very high values of river discharge. This is the Indus River, which been impacted the most by the Pakistani floods. So if you Google the Indus River, what's the average like normal river discharge? It's around 5,000 cubic meters per second, if I'm not mistaken. So here you can see that the max value here is 6,000, so it's bigger than the average discharge. But this actually is this value is normalized for all the layers here. Like for example, I can put here, like in the beginning of summer, it was not that bad, or like you can see. But if we right click and go to properties, we will see that actually, let me go to, yes, if you go to max value here in bands, you can actually see that the max value is 25,000, almost 26,000. So you can imagine how much bigger, sorry, river discharge was than the average one. So that's what was the reason to choose explicitly this time frame. So here, what we can see is a lot of rivers, so big area, covers several countries, not only Pakistan. So next step, what we did, we wanted to have only the data only on the Pakistan itself. So for this this layer, you might, I hope you see, because it's a bit specific, with blue lines. This is layer with country borders for the whole world. It's external layer. You can export it. It's all given in a PDF file, and we transform it to polygons. So now we have basically polygons representing each country. And to do this, you can go to polygonize in vector, if I'm not mistaken. Yeah, here in vector geometry polygonize, you can create from lines polygons. And then from all these countries, only all the polygons, only one polygon has been chosen. So the Pakistan one, I can tag it, and it's been clipped. So this raster layer, the one behind you see for the 30th of August, it's been clipped according to the to this polygon. So as a result, we have this. So basically now we have our river discharge, which are interested in, explicitly in Pakistan. So we don't see rivers that are not belonging to it, for example. And to do this, to clip the raster layer with some mask, you go to raster, you go to extraction, clip raster by mask layer. Here you put your raster layer, you put your mask, and yeah, you choose maybe if you want to, yeah, some optional features, you run and close. So for this exercise, what we want to do is to find out how far away the major cities of Pakistan are from this river, from the Indus River. So we found this open source database with the major cities of Pakistan. So it's only, if I'm not mistaken, it's 150 or something like this of cities. And here you can see, I think, yeah, there's information about the name, the latitude, longitude, and the population. So you see these circles and these marks, they represent population of cities. So the darker circle represents more dense in terms of population city. So here you can see that some cities are very close to rivers. Well, most of them next to rivers. So as we want to know, we want to distance to this overflooded river, the Indus River. Of course, this information is not going to be explicitly precise because we see that our resolution is, you can see that the pixels are not very, very coarse. So it's a bit not very fine mesh, let's say. So it's going to be not so maybe not very representative if you really want how to say, like in terms of Dade River really like went out of banks and went to the cities, for example. So, but we're just here to show you how to use the data we have in QGIS and how to use several QGIS features functions. So to find the distance between this river and the cities we first need to vectorize our layer because it's raster layer, so it's pixels, as I said. And for this, we have this, and it might be not very, let me, okay. So first thing that we did, we vectorized this layer, this raster layer, by basically going to raster, conversion, polygonize, raster to vector. So you choose your raster layer, and it converts it to vector layer. So basically, each pixel becomes a polygon. So like this, we have this. You can see a lot of polygons. And what I did after, I go right-click, filter, and I put this expression. So this expression is exactly like this value is the normal average river discharge of this river, of the Indus River. So we do the, if we want to find the discharge river which is bigger to show the, yeah, okay, so here it shows us that during this date it was exactly this, these little pixels. And next we want to find the distance, but before, after we polygonize and we convert from raster layer to vector layer, we have a lot of features, a lot of polygons which are not valid. So there's some error which happened to one or more or several polygons, and you won't visually see it like yourself, but when you will continue doing some special analysis, you will use some features and functions of QGIS, you will see that QGIS will tell you, I cannot work with that because you have some errors. Please fix it before proceeding. So to do this, we fix our geometry. As I said, like this is a fixed geometry which has no like visual difference for us. And to do so, we basically go to fixed geometry. There is one function here which you use, which you put your polygon, which you want to, your polygon layer, which you want to fix, and you run, and you have this. So next, what we want to do is to find the distances. So now we see that basically these little polygons, so we can find, so now it's not a pixel, it's a polygon, so we can find the distance between these little polygons and the closest to them cities. For this, we go to nearest hub. Okay, so in vector analysis tab, there's a distance to nearest hub, line hub, which we're gonna use, and use a source layer and destination layer. Yeah, like important notice why we converted our raster layer to vector layer is because this function works only with vector layers. So you can see here, you can see that it's polygons, it's lines, it's points, but yeah, no raster layers, sorry. So after this function is done, you will see something like this. So this is basically, these lines, they represent the distance. They represent basically the line, the closest path from this specific city to the closest to them polygon representing the river, part of the river which is overflooded at this point, at this moment. And if we go to right click, open attribute table, we will see here the last column, how distance. This is our distance in kilometers. So if you want to play more with it, you can put some filters for, I don't know, less than 1 kilometer close to the river and so on. So that was it for the first exercise. I'll show it. Yeah, I know it's very fast and maybe it's not very clear, but yeah, we have a tight timing. So, okay, so for second exercise, we're going to work with satellite images. And for this first, I'm gonna, like here we have a background layer and QGIS doesn't have a, how to say, default background layer. You add it yourself. So we usually add this one because this is pretty much enough. But if you go very like zoom in, you see that the image is not very fine. So what I did, I imported another layer, raster layer, and our background layer, which is basically our Google Maps, basically. So you can really go quite like zoom in quite close and see quite good resolution of a picture. And we need is just to see basically river and how it changes. So here you can see that this is exactly the river we are interested in, the Indus River, here. And what we're going to do, we're going to use images, satellite images, which are going to be imported as raster layers. So for this, we chose 2 different days. So one was in, if I'm not mistaken, it was 27th of February in 2022. So before the floods, way before the floods. And the second was after, during, let's say, floods. It's 30th of September. And so for example, I show you the image. Let me see. Okay, it's here. So of course, it's a small satellite image, just one specific area where we can see the river. Here you can see it. By tagging and tagging, you might even see the difference between what you can see from Google Maps. I don't know exactly the date of this map has been created from pictures taken, but we can see that the river changed. And also, I'll show you this. So it's after or like during, and this is okay. It takes a bit time. This is before. So this is the usual the true color pictures. We also will need these images, these 2 bands. So it's a band 3 and band 8 of a Sentinel-2 satellite. And we need these 2 specific bands to calculate our normalized difference water index. So this is an index which allows us to spot water bodies on satellite images. If you want to read more about this, there's some info given in a PDF file, and there's also internet. You can go and explore more. So yes, we have also these 2 bands, which all these pictures were imported very easily by layer, add raster layer, and you just navigate towards the directory where you have the images, and yes. So the next step was to calculate exactly this NDWE, so water index, and that's the resulting one. So this is how it looks like, the resulting index. And to calculate it, you will need to use a raster calculator here. And in raster calculator, you basically put the formula with your raster layers to have it. And I don't remember exactly the formula right now, but I think it's band 3 minus band 8 divided by the sum of band 3 and band 8. Maybe the order is switched. Cannot say right now. But it's of course given in more precise in a PDF version. So after this formula is used in calculation, we will see this for this picture for the 27th of February, so before floods. And this is after, let me just show you how it looks like, yeah. And next, what we need to do is to create a water mask. So exactly the, like to extract pixels which are representing only water, nothing else. And for this, we also use raster calculator, and this I remember for sure. This one, you put this water index which is equal to 1. So pixels that are representing water, they are having value 1, and pixels which are representing something else is 0. So like this, we have two results. So this is our water masks for 30th of September. So you can see there's only black and white. So white's water, black is everything else. And I have the same for February. Yes. So for example, even now you can see that in February, it was like, let's say, less water pixels was detected than for 30th of September. You can see the difference. And the last step is, what if we want to have these pixels, these like water bodies, but like polygons. So we can again easily do it by the thing that I already showed you. So it's vectorized. So it's from raster conversion, raster to vector, and you choose the water mask as an input layer because it's a raster layer. We know it's pixels, and at the end we will have. Let me untag everything. We will have this, and of course it's already filtered, as I already showed you. This is the filter. So I showed only the polygon corresponding to river, because if I yes, so after you vectorize, you have this full area being vectorized. So all pixels with value 0 and 1 was vectorized, and when you put the condition, you can have only a specific subset. Maybe it takes some time, or I don't know what happened. Okay, let's filter it again. Okay, yeah, now it worked. So now you can see the rivers, and here you can like check it how it corresponds to the background layer. And also, if you see what was before, okay, QGIS is a bit tired. I think it's a bit slow. Let's give it some time. Okay. Yeah, okay. So yeah, here you can see the difference between red. Yeah, okay. Red is our how river looked during before flooding, and in orange how it looked during/after flooding. So yeah, here you can see the difference. You can perform more calculations and more analysis if you wish to, and you might see that, especially like here, we won't compare, but for example, if we leave our February polygon and turn, where is it, represent also a picture. Yeah, you can see, for example, if we untick our vector, we see that, yeah, this is water, right? This like greenish colored one, but we also consider that this stuff might be considered as river, right? It's probably some sand or like something that's maybe at this exact date, so it was at 27th of February, wasn't covered with water, but like in 2 days it's going to be covered with water. But of course, for the image, satellite image, after we calculate this water index, it already is not considering it as a river, so it shows like less. And sometimes, yes, you can see maybe that it doesn't consider all water pixels, so it's yeah, like this water index, how to say, might be more precise. So that's a standardized index, but you can see that sometimes it might not work perfectly. So that was mostly it. That was very, very quick. I hope it wasn't too hectic. So yes, I just showed you how to briefly how to use some raster data from WEkEO service, satellite images, and just some data about, for example, we use this river discharge, how to map it, how to vectorize it, how to do some calculations. And yes, you are free to reuse this example for something else, or even push forward, repeat this example, and maybe calculate even more exactly for this application.
Thank you, Daria. It was indeed very quick, but I hope this was just enough teasing for people to play around with the data. And now we have a few questions for you. Let's see. Can you indicate the raster source of the river dischargers?
Yes, this is okay. I don't share a screen, right? Okay, well,
you can if you want.
Yeah, it's just no. I need to find it. I think it's if you go to WEkEO platform and you just go to add new layer and put river discharge. I think it's gonna be basically like the first one or something.
On
Never
the
mind.
filter.
Yeah. So, but there's also like the precise link for it is gonna be in PDF file. All the links are given, and also all the data, like not only the links, but also like which area has been downloaded, which time frames, and so on.
Yes, great. Another one. You're placing Sentinel data over Google Map. What is your comment on image distortion, such as mismatch in locations, because they are different satellites data? Is that right?
I'm not getting. Okay, so yeah, I changed the background because there's in our tutorials we usually use one specific background, which has not very fine. It's not very fine resolution actually. Like you don't see the river basically if you want to see it. And for this tutorial, I just used another background like Google Maps. You can use whatever you want. And it was mostly also to show that there is a number of possibilities of a background. And it was just to see basically like more features. And and mismatching locations, I don't know. I didn't check this point, but I think they were quite on point together.
Okay, thank you. And now we have, well, so it's a comment and several questions in once. So I'm beginning in GIS and QGIS. What is the significance of vectorization? So it is kind of a broad question. I don't know.
Yeah, I'm reading.
So when we do analysis of a river, what is the meaning of vectorization?
So basically, in QGIS, you have to, let's very like strictly separate layers. There are two different types of layers. There are raster layers and vector layers. And based on that, QGIS have different features, different functions, different options you can work with, specifically for raster layers and for vector layers. And there are many functions which are like they're intertwined. So basically you can use the same, like you can have the same result from pixel, from raster layer with pixels, and from vector layer with polygons. but some features are only available if you work with raster or only with polygons, so with vector. So that's basically the whole point of vectorization, to access other features, other features which are not available for raster layers.
Great. And I think that's all the questions for you, Daria.
Okay.
Thank you very much. And yes, like Daria said, more information will be on the PDF and on the Padlet. Just to remind you to have access to the Padlet, if you take a look at the top of your screen, you will see a yellow button saying WEkEO workshop material. That's where everything is going to be. So thanks a lot, Daria, and thank you everyone who has presented today. Ergane, David, Julia. I think Julia is no longer here with us, but yes, thank you for your participation. It was very interesting. I found it very interesting. I'm sure our participants as well, by the comments we have seen. So yeah, keep practicing, and we will see each other on our debriefing session.
Yes.
It's going to be on the 5th of April.
Yeah, let's just not forget to have the second part of the survey. We have some questions for you.
This survey, you will also be able to access it actually on the Padlet, where you will have all the questions over there. Yes, that will be great if you could fill it in. Thanks a lot for everyone's participation again, and we see you on the 5th of April.